So far, we've taken recursion and gone to an explicit formula dealing with our lines, our linear equations. Okay, and when we did that, all we really did was we took the initial term and put it in for like our previous term, like our y-intercept, right? And then with our rate of change, it's going up 3 each time. We threw like the n on the end, or really when we do it in terms of a linear equation, this u sub n became y, and we'd say equals, well, this was our 3x, our slope of 3, right? And it has a plus 5 for a start, for its starting value. So this would be an explicit equation for linear, right? Our linear equations. Well, we can do the same thing for exponential equations, and that's going to deal with our geometric sequences. So over here we had arithmetic sequences, but we can write an equation, an explicit equation for our geometric ones now. Well, it kind of works the same way. This 3 goes in for the previous term, and instead of being multiplied by n, instead of having the n right here, let's think about this. That would be if like it went up 2 each time, but it's being multiplied by 2 each time. So what would I do with the 2 if I wanted to multiply it like 5 times? I wouldn't do it times 5, I'd do it to the 5th power. So the n really goes to the exponent now. And so if I were to rewrite this in terms of y and x, it would be what? Y equals 3 times 2 to the nth power. So one question, do not ever make this mistake. I know you're going to be tempted to do it. Is this the same as y equals 6 to the nth power? Not a chance. Nope, 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 nope. Why? Because exponents have to be done before multiplying. Okay, so don't do that. Do not multiply before your exponent. So you have to leave it like this. Okay, you cannot multiply the 3 times the 2 when there's an exponent on the 2. All right, so just be careful with that. Okay, so let's use this. Let's take a look a little deeper now. Let's see what the graph would look like in this case. All right, so I'm going to start with, these are really my x's and y's in the case. So if I started with 0 for x or n in this case, what would I get for the y? So if the initial is 3, and each time we go up 1, we're going to multiply by 2. This would become 6. This would become 12. This would become 24. If I went backwards, I'm really dividing by 2. So if I went to the negative first spot, what would I get there? I would get 3 over 2. If I went to the negative second spot, I would get 3 over 4. So it's getting smaller, right? Well, if I look at it in terms of my explicit equation, if I did y equals 3 times 2 to the xth power, that's really putting in these values. So for example, if I put in 0 for x, y equals 3 times 2 to the 0. Well, what's 2 to the 0 power? That's really 1, and 1 times 3 is 3, so that's where that comes from. So let's just go ahead and graph these points. So I got 0, 3, 1, 6, 2, 12, 3, 24, and then it looks like I got negative 1, 3 over 2, so that's like 1.5. And then, oh boy, it's getting closer and closer. If I kept going in deeper into the negatives, like let's say I plugged in, like negative 50 in for x. I put in a negative 50 here. Would I get a negative number? No, I just get a really, really small decimal or a really, really small fraction. So this never becomes 0 or negative, so it just kind of floats right there. And then it exponentially increases, right? See how I use that term exponentially? Because it's got an exponent, correct? Well, let's just try some of these exponential expressions and see what they mean. So let's go ahead and type in 2 to the negative 5th power into our calculator. 2 to the, so now I got to use this caret button all the time, so negative 5th power. And I get, a decimal. I don't like decimals. Let's go to a fraction math, change to a fraction. 1 over 32. So this gives me 1 over 32. Well, if we remember our negative exponent rules, it really just puts, what it does is, to become positive, I got to think about it as a fraction. So if I take 2 to the negative 5th and make it as a fraction, so 2 over 1, to make it a positive exponent, you have to move the whole thing to the other side of the fraction. So this is really 1 over 2 to the positive 5th power. Well, and 2 to the 5th power is 32, so that's where we get that 1 over 32. Okay, so negative exponents just moves it to the other side of the fraction. Hopefully that's a rule we remember from our Algebra 1 days. Okay, let's try the next one. 25 to the 1/2 power. So I'm going to go 25 exponent. And sometimes it's nice to put this in parentheses just to be safe. So 1 divided half. I don't think I need it, but I'm going to hit enter here. I got 5. That's weird. What else is 5? What else can I do to 25 and get 5? Yeah, if I took the square root of 25, I would get 5. Okay, and what you're going to find out in a section or two here is that this can really be written like this. The 1 stays with the 25 to the first power, and it's really the second root of 25 to the first power. So what happens is this 1 stays with the 25, and this 2 goes with the index on the root. We're not going to look too far in depth with that because we'll get to that in a few sections, but that's what it really means. But I can use my calculator to check all these guys, right? Let's try the next one. 9 to the 1.5 power. 9 to the 1.5. And I got 27. Interesting, okay. So I got 27. Well, how do these relate, the 9 and the 27? Well, they're both, multiples of 3. So if I think about it, 9 is really 3 squared, and 27 is really 3 to the third power. So, and if I rewrote this 9 to the 5th, or 9 to the 1.5 as like 3 over 2, and applied my rule I just looked at up here, how could I write that? Well, I would write 9 to the third power and take the second root of that. The other part is, this can be flip-flop. I could actually write this as the second root of 9 and take that whole thing to the third power. So I could write it either way. Same thing with this guy up here. I could have wrote second root of the 25 to the first power. They both work. Well, what's the square root of 9? 3. And what's 3 to the third power? 27. Okay, so a lot of things. I'm throwing some new things at you, but we're not going to go too in-depth because we'll do that later. So if I just look at that, knowing the rules I've just applied, what would I get for 16 to the negative 3/4 power? Well, the negative really means I'm putting it on the bottom part of the fraction. So that would be 16 to the 3/4 power. And if I applied my rule that I've just done, it's really 16 to the third and the fourth root of that. Kind of confusing, right? Let's go ahead and type this guy in. Let's just type the whole thing in here. So I'm going to do it from the beginning. 16, 1.2, our 0.125. Let's change to a fraction. 1/8. So that is 1/8 right there. All right, so tricky stuff, right? And if I think about this, if I rewrote this guy as the fourth root and 16 into the third power, well, what number times itself 4 times gives you 16? Yeah, 2. 2 to the fourth power is 16. So then really this whole thing is 2. And what's 2 to the third power? 8. So that's really where that 8 came into play. I know I'm kind of making this confusing. We're going to go in more depth of this in the next couple sections, but right now we're just kind of getting an intro into what those really mean. All right, let's go to our parent graph. Okay, and the reason why we don't have a 1 to the x power is if I took anything, if I plugged in like 1, 2, 3, 4, any of this stuff, this would all be 1. So that's why we don't use 1 to the x power. So we go to 2 to the x power for our parent graph. Okay, and I'm going to start with like -2, and I'm going to go up to maybe 3, just to get some looks here. So let's just start with the easier stuff. Anything to the 0 power is 1. 2 to the first power is 2. 2 to the second power is 4. 2 to the third power is 8. And then if I work backwards, divide by 2, 1/2. Divide by 2 again, 1/4. If I divided by 2 again, I'd have 1/8. So on and so forth. And let's go ahead and graph this guy. So I got -2 and 1/4. It's really close here, really close here. 0, 1. That's a key point. 0, 1 is our new key point for this parent graph. All right, get that down. And then 1, 2. Here's our other key point. So these guys are both key points. That 1, 2. Okay. So this first key point will be for our shifts, and this other key point will be for our stretches. There we go. And then let's finish it off 2, 4, 3/8. Drawing my line, doesn't cross the x-axis, doesn't get to 0, and it goes up like this. Good. Perfect. What if I did the domain and range here? Domain, x values, all of them work, all real numbers. What if I did the range? What about my y's? Well, my y's never get to 0, so all my y's are greater than 0 in this case. So to use this with our story problems, especially growth and decay, this is how we use it. The a, we have this nice little formula. Y equals a times bx, a times bx. So a stands for our starting value, and b is our common ratio, right? And we've dealt with common ratios with our exponential recursion, our geometric recursion sequences. And just remember, growth always occurs when b is greater than 1, right? When this guy is bigger than 1. So think about this. This is always going to be like 1 plus, right? Especially when we deal with percents. Remember, percent as a decimal. And the other one is going to be like 1 minus. And there's our percent. So we'll see that on our story problems here for our decay. So this deals kind of with our recursion a little bit. So for example here, the growth rate of an urban geese is 14%. If there are initially 42 geese, how many can be expected 5 years from now? So here is our nice little formula to use. So y equals starting value 42. And then what would be our common ratio here? Well, it's going up 14%. So remember, this is where we take our 1 plus our 14% as a decimal, which is really what? 0.14. So it's like you're looking at 114% of 42 each time, right? That's how you increase 14%. And we're looking for 5 years, right? So this would be our time right here. And all I do is I go ahead and plug this into the calculator. Just make sure to type it in all at once. What you don't want to do is times these first. Do not times those first. If you're going to type them in separately, make sure you do exponents first and then multiply by 42. But in this case, I think I just like to type it in all at once so I don't make a mistake. And I got 80.867. And what are we talking about? Geese here? So I'd say about 81 geese. There we go. We don't want a partial geese. How about this? The recent decline in Indian owl population is blamed on the popularity of Harry Potter. Crazy. If the decline is 10% each year, about how long will it take for the population to be only half of what it is? All right, so let's look at our equation. Y equals y. I don't have a starting value, so I'm just going to leave it as a for now, times, well, b. So now what's happening? We're going 1 minus 0.10 or 0.1, right? And then we don't know our years, so it's still x. We're trying to find what x is. Well, in this case, when you decrease by a certain rate exponentially, it doesn't matter what your starting value is if you're looking at half of it. If I started at 500 and I look for 250, that's the same thing as starting at 100 and looking for 50. This means the exact same thing. So pick numbers that are easy to use. So I'm going to go 150. So 100 is my starting value, my a, and half of that is 50. And this really becomes what, 0.9? All right, let's simplify this guy. How would I get this? I want to try to get the x by itself. I'd have to divide by this 100 to get it to the other side. So I got 0.5 equals 0.9x. And right now we haven't done anything to learn how to solve for an exponent. We will next chapter. But before we do that, we still want to get some in-depth looks with our exponents. So we're not going to learn how to solve for that yet. So what we're going to do is we're going to grab our calculator, and we're just going to take 0.9 to some powers and see when we can get about 0.5. So I'm going to take 0.9, and I'm going to take it to like the 4th power and see what I get. Do I get 0.5? Not quite. Let's try it again. 0.9 to the 6th power. How about? That's getting closer. So 0.9 to the 7th power. Pretty good. So it's somewhere in between there. So I might say like 0.9 to the 6.5. I'm going to go right in between 6 and 7. So that's pretty close. So I could say about 6.5 years. Another way to do that would be like this. I could take 100 and multiply it by 0.9 because that's really what's occurring, right? And I want to get to 50. I want to get to half the size. So there's 1 year. So if I multiply, so there's 1 year. So I'd multiply my new total by 0.9 again. There's 2 years, 3 years, 4 years, 5 years, 6 years, 7 years. So I can tell it's somewhere between 6 and 7 years. it's a little bit easier to make this equation and try to get something that's a little bit closer to 0.5 to be more exact, but either way really works, okay? And the same thing is going to work if we decide to double something. So for example, let's just pick one of these to do. I'm going to go with, let's just solve for 4% interest here. How long will it take for an investment to double? Well, let's just make up some numbers again. So let's say my investment is starting at, let's go with $1,000. So if my starting value is 1,000, and I'm looking at 4%, so plus 0.04, right? Because 4% as a decimal is 0.04. And doubling that would get to 2,000. So if I divide it by 1,000 here, so really I want to figure out when I get to 2, don't I? So 2 equals 1.04 to the x power. So let's take 1.04 to some powers here and see how close I can get to 2. 1.04. Let's try 10 years. Let's try 13 years. Closer, 1.04. Let's try 18 years. Ooh, that's really close. 1.04. Let's go like 18 point. Oh, so 17.9 years. Even closer. So it's about almost 18 years. So I'm going to say about 18 years, or a little less than 18 years for 4%. Okay, and obviously if I did 8% interest, it'd be a little bit sooner. If I did 2% interest, it'd be a little bit later. But it doesn't matter what my starting value is. Doubling is the exact same time no matter how much you put in to be able to double it. And that's about that. We'll keep building on our exponents as we go through this chapter.